Hello everyone, welcome to Driven Life, Math and Physics. So today we'll begin looking at uniform circular motion. And so we'll introduce the topic, and hopefully I think there will be a few parts of this topic that we'll produce. So we'll have part 1 and maybe part 2 on, and if things we don't manage to cover everything in 2 parts, then we'll have a part 3 as well. But otherwise, let's get into it. Now, when it comes to uniform circular motion, I think this is something that we have experienced in our day-to-day lives. I think you have ever seen an athlete running in a circular path. I think we see this a lot during the Olympics, where you see people competing maybe in the 100 meters or even 200 meters or whatever distance they're running, especially the marathon, where not really the marathon, but where they have to run so many laps. What you notice is that as they are running around that circular path, they sort of lean inwards. Okay, they lean inwards so that they can continue to move at that circular path. That's the first example we're saying here, to say an athlete running a circular path leans inwards towards the center. This is because I want to continue to maintain their circular movement. The second example that maybe you may have seen in your day-to-day lives is a motorist negotiating a circular turn. What you also notice when someone is maybe driving a car, maybe especially when someone is on a motorbike, okay, you see them leaning inwards as they're negotiating that turn. It's because they want to maintain their circular movement. Now, what is uniform circular motion? Now, the things that I want you to take note from this phrase, uniform circular motion, is the word uniform. Okay, uniform. This means that something has to stay constant in this type of motion. That's why it's called uniform circular motion. When you progress to college, you will cover something that is called non-uniform circular motion. But at this level, we only look at uniform. Now, the other phrase, or maybe the other word that I want you to take note, is this one, circular. Okay, that tells us that this type of movement is not linear. Okay, you remember the topic we covered in Form 3? It's linear motion, meaning that it's motion in a straight line. Okay, it's motion in a straight line. But in this case, we're talking about motion in a circular path. That's why it's uniform circular motion. Now, by definition, uniform circular motion is motion along, first of all, it's motion along a circular path. Motion along a circular path in which there is no change of speed. So we know exactly what remains constant, and that is speed. The magnitude of speed stays constant, but the thing that changes is direction. Okay, so this is motion along a circular path in which there is no change in speed, only a change in direction. Okay, that's uniform circular motion. And so this thing will come very much, it will become very vital as we go towards the discussion on the centripetal force and centripetal acceleration. But for now, I want you to just understand that it's motion along a circular path in which there is no change in speed, only a change in direction. So I ask a question here to say, why is it called uniform? Okay, it's because there is no change in the magnitude or size of the speed, hence the name uniform circular motion. Okay, now let's progress from there. Now, don't worry about this. Maybe it looks strange, maybe it looks busy on the page, but this will make sense to you very soon. The first concept that we'll discuss on uniform circular motion is something called angular displacement. Now, I will draw your attention back to linear motion so that we understand this properly. Okay, in linear motion, we discussed a concept called linear displacement. Okay, displacement in a straight line. What we said was that if a person or an object or a car moves from point A to point B, okay, that means this person or this object has displaced from point A to point B linearly. Okay, this is linear displacement, the movement, a distance covered in a particular direction. This is linear displacement. That's what we discussed in linear motion. Now let's take, I want you to look here. Okay, I have a circle here with let me just remove this part. Okay, let me just remove this part so that this makes so much sense. Okay, now let me remove this part. Okay, let me just redraw this, I think. Okay, so let's take, for instance, we have a circular path. Okay, and the center of that circular path is O. The radius of that circular path is OA. So the radius joins to point A. This point A is the point where this person is starting from. And then let's take this person moves from point A and then displaces to point B. Okay. And what you have to understand is that when we're talking about a circular path, we will talk in terms of the length of the arc this person has covered, because this path is not straight, it's a circular path. Okay, so the length of the arc they have covered, this one, is what we'll call S. This is arc length, equivalent to how much someone has displaced. Okay, it's not linear, but someone has what? Displaced. That is arc length. Okay, but now the concept of angular displacement, as the name suggests, okay, the concept of angular displacement, this is the radius OA, as the name suggests, is that it's a displacement that can be described using an angle. Okay, angular displacement, okay, is described by the angle swept through by the object or the person who is making the movement from point A to point B. Okay, this is displacement that can be described by an angle. Okay, that is very important. This is why angular displacement, if we were to describe it in our scenario here, will be described by the angle theta. In other words, the amount of distance this person has covered from point A to point B can be described by how much angle we have swept through. Okay, that angle we have covered is what we call the angular displacement, and the symbol for angular displacement is theta. Okay, we describe it in terms of the angle swept through in covering a certain amount of distance around a circular path. Okay, now let's look at the connection between arc length and angular displacement. So we talked about it here. I think one of your books in your syllabus is Django, where it sort of gives an indication to as if arc length is the same as angular displacement, but they are not the same. Okay, what I want you to understand is arc length is a distance around the circular path that is covered, but now angular displacement is the angle covered in covering that distance, and this angle is measured in what we call radians. Okay, radians is a unit for angles, the way we use degrees, but there's also another unit called radians. So how we describe angular displacement is by using radians. It's the angle that is swept through in covering a distance, in this case from A to B. So we need to know the connection between arc length and angular displacement. Now, something that is very much important for me to mention before I go there is this. Okay, I want to mention this. Now I want you to look at this. Angular displacement here, angular displacement is theta. It can be described by an angle and is measured in radians. I wanted us to really understand that. Very important. Never forget, angular displacement, it has a symbol theta, it's measured in radians, and it's the angle that is swept through in covering a certain amount of distance around a circular path. Very important. Now, arc length and angular displacement. The first point I want us to understand is that if the length of an arc, maybe of the arc AB, is equal to the radius of the path, what we're saying there is that if there is a scenario, okay, I want you to see here, if there's a scenario where OA, which is equal to OB, is equal to S. So now remember this. S is the arc length, okay? If it happens that the arc length is equal to the radius of the circular path, what has been discovered is that the angle swept through is exactly 1 radians, okay? If the length of the arc that you have covered, is equal to the radius of that circular path, the angular displacement that you will cover at that point is 1 radian, okay? 1 radian. It's very important because this is foundational to what we're going to look at. So if arc length S is equal to the radius of the circle, or maybe the circular path, the angular displacement at that point is 1 radian, abbreviated by rad, okay? All right, and then we say that if now it happens that the arc length that you have covered is 2 times the radius of that circular path, the angular displacement at that point is 2 radians, okay? 2 radians. Now that means if S is equal to 3 times r, okay, the angular displacement will be 3 radians. Can you see a pattern here? What you will notice is that the coefficient, or maybe the number in front of the radius, is what happens to be the angular displacement. Now let's look at it some more on the other page. Very important. We'll come back to this soon, okay? We'll come back to this. Now what we're saying is that if S is equal to r, the angular displacement is 1 radian. If S is equal to 2r, the angular displacement is 2 radians. And if S is equal to 3 times radius, at that point the angular displacement is equal to 3 rads, okay? And if S is equal to 4 times the radius of the circle, the angular displacement at that point is equal to 4 radians, okay? But let's take, now you have to remember, S is the arc length. So if we cover a distance around the circular path of 4 times the radius, the angular displacement is 4 radians. Very important. But now let's take, we have covered the whole circular path. That means the whole circular path, the whole arc of the circle. When we say the whole arc, it means we're talking about the full circumference of the circle. If we have managed to cover the full circumference of the circle, which is 2 pi r, okay? The circumference of the circle is 2 pi r. If we have moved from point A, then back to point A, if it has happened like that, and the arc length covered is 2 pi r, which is the circumference of the circle, then the angular displacement at that point, remember, if it is 2r, the angular displacement ended up to being 2. If it's 3r, angular displacement ended up being 3. If it is 4r, the angular displacement ended up being 4. Okay, so what if it is 2 pi r? Then the angular displacement will be 2 pi radians. Okay, at that point we would have swept through an angle of the value 2 pi radians. If you're moving the whole circumference of the circle, that means we have covered 360 degrees. So that 2 pi radians in terms of degrees is actually 360 degrees. Okay, so what we're saying is that 2 pi radians is equal to 360 degrees. This is a very important thing for you to remember. Okay, it's a very important thing for you to remember. Now let's go back here before we continue. Now what you will notice in this sequence is that the 3 before the r, okay, is actually the angular displacement. Hence we can come up with a formula that arc length, or the displacement around the circular path, is theta times r. Theta in this case is the angular displacement. Okay, S is the arc length, which is the displacement around the circular path. Okay, and then r is radius of the circular path. Remember, arc length is not angular displacement. Angular displacement is the theta. Okay, it's the displacement described by an angle. Okay, very important for you to remember.